Hello, my name's Allan Jude, and I'm the CTO at Klara, and today I'm going to talk about the ZFS vdev properties feature that we contributed to OpenZFS. So this work originally came out of discussions that I had with various people at both the ZFS User Summit hosted by Datto and the OpenZFS Dev Summit later that year, both in 2018. And based on those conversations, there were a few needs that were identified. The first was we needed a way to store just ancillary data about each disk, whether that was just what the model of the disk was, or some information about the disk, or where the disk was, or something about it. And we needed a way for administrators to express more of how they wanted a disk to be used and other things about the disk. And then lastly, there was the problem of mixed configurations. If you have a system with one pool that's made up of flash media, like SSDs, and one pool made up of hard drives, a lot of the tunables you have in ZFS are system-wide, right? They're sysctls or module parameters. And that means that you can't tune the device queue depths to be higher for the SSD pools to get more performance without also making them higher for the hard drive pools, resulting in worse latency. And being able to control both of those was part of the idea. Of course, that's the one part that's not actually done yet. So our motivation here was that ZFS properties are a great way to manage the settings in ZFS. Anybody who's used ZFS at least somewhat is very familiar with properties. Just ZFS set compress equals Z standard on a data set, and that's all there is to it. It's easy to read and write properties and figure out what's going on and see how they're inherited. And those properties apply to file systems and volumes and snapshots and so on. And there are also pool properties, although not that many of them. And the ZFS tools provide a great UI for those properties in both human by default, or with a couple of flags, you can get machine readable parsable stuff, right? Don't scale the numbers and show me megabytes, always write them in bytes. Separate all the columns with tabs instead of making them line up nicely, and so on. It makes it really easy to parse the output of ZFS. So we wanted that same thing, but for VDEVs. So how do VDEV properties work? We use basically exactly the same interface as a pool property, except for after the name of the pool, you specify the name of the disk that belongs to that pool, and then you can get and set properties just like you would on the pool. There's a special VDEV, well, not a special, there's a keyword you can use, all-VDEVs, so that you can get a certain property or all the properties from all the VDEVs. So that would be like zpool get some property pool name all-VDEVs, and it will get that property from all the VDEVs instead of just one. We also took the opportunity to expose a bunch of read-only counters that ZFS keeps about each VDEV, and they were just internal and you had no access to them. So we exposed those as properties as well. They're just read-only because you can't change them. Then we have some writable properties that allow you to control things about the VDEV. That can be very useful. And then we added user properties. So you can make up your own properties and store a bit of data in there about each VDEV. So what properties do you get? The first one is a comment. So every VDEV has a short text string where you can store some information about it. That was already there, I just hooked it up. One of the other writable properties is the path to the VDEV, so what device it actually is. We'll come to a bit later how you can use this one, but it solved a particular problem I had very frequently, being able to change that. There's also an allocating property, which again I'll explain a bit later. It allows you to queue up multiple devices for removal without being very inefficient. And then we have the user properties. So the same way that you can set arbitrary user properties on a data set, normally done with some namespace property equals value, you can set user properties on a VDEV. And then, as I mentioned, it doesn't exist yet, but in the future we would like to see more of the sysctls in the ZFS underscore vdev or ZFS.vdev mib tree move to actually be vdev properties so that you can control them per pool. And it also has the advantage of that configuration would persist even if you move the pool to a different system where the current sysctls do not. But what properties can you read? This is where all that internal stuff comes out. So you can get the device's ID, which can be different depending on your operating system. You get the physical path, which on FreeBSD, Geom will have populated with a bunch of information. Between the physical path and the enclosure path, you can actually see if you have a SES backplane the disk plugged into, it'll actually tell you like the slot number the disk is in and all that kind of information. The field replaceable unit is from Solaris. It's supposed to, I think, have the model number of the disk. We might have to do some work on the Geom integration code with ZFS to plumb out a few more of these values. But each VDEV also knows who its parent is up until it's a parent of the pool. So if you have a mirror VDEV and it has two disks in the mirror, if you get the properties of one of the disks, it'll say its parent is mirror-0 or mirror-3 if it's the fourth mirror, and so on. So you can actually understand the hierarchy of the VDEVs from these properties. So if you're looking at the disk VDEV that is a part of a mirror, it will have 0 children. But if you actually get the properties of the mirror-0 VDEV, it will say, hey, I have 2 children and they're called 80A0 and 80A1 or whatever. You can also see the size and how much free space there is for each VDEV. Not all of these will make sense. If you're looking at an individual disk in a RAID Z, it will not have a size or a free because the size and the amount of free space belong to the parent VDEV, not the leaf disk. How much space has been allocated on it. The boot size property, this one comes from Solaris. I don't think it's implemented in OpenZFS yet, but if you have ZFS manage the partitions on your disk, this allows you to set aside an amount of space for your EFI boot partition. The A size is the allocated size, so how much space ZFS will use off the disk. ZFS divides your disks up into metaslabs, and each of those metaslabs is a fixed size, and so there's a rounding error means the last little bit of your disk isn't actually used, so the A size is the actual amount of space on the disk that ZFS can allocate. And P size is the physical size. You can see the A shift, which is basically the sector size, the allocation power of 2, so all allocations will be a multiple of that number. You can get the stuff you would normally see in, say, zpool status, so the number of read or write or checksum or initialize errors. But you can also get the number of IOPS of each type, so read, write, free, trim, etc., IOPS, and bytes. So you can see exactly how many IOPS and how much has been read and written to each VDEV. These are internal counters from ZFS, so they're reset to 0 every time you import the pool. So when you reboot or you export and import the pool, so they're not persisted, but while ZFS is running, it adds up to these counters all the IOPS and bytes it's ever done, and you can extract those and use them for monitoring, and I'll show an example of that later. The expand size, if you have a disk and you in a VDEV and you've replaced it with a larger disk or something, this will be how much space ZFS could grow this VDEV if you told it to with zpool online-e or setting the auto expand property to on. The parity, so if you have a RAID Z, if you get the properties of the parent, the actual RAID Z whatever dash number VDEV, it will tell you its depth. Is it a RAID Z1, 2, or 3? You can see how fragmented each VDEV is, how much space it has, its GUID. Every VDEV has a unique GUID, including the leafs. So the mirror itself will have a GUID, and then each of the children of it will have a GUID. And then you can see the state of a VDEV. Is it online, offline, degraded, working, replacing, etc. And then lastly, there's a property removing, which will be on if that device is currently in the process of being evacuated to be removed from the pool. So if you do zpool get all from pool name and do all-vdevs, then you'll get output like this. And you can see, that vdev is 64% full. It's 16 gigabytes. Of that, 5.69 are free. You can see the path was dev88.1, and the device ID was, it's a VirtualBox disk, and there's its serial number. And the physical path, you can show how it's connected via PCI. Its parent is the pool, so it's a single disk top-level VDEV, and it has no children. And you can see that it's done 505 read IOPS and 813 write IOPS, a couple megabytes or whatever, basic stuff like that. But by getting the machine-readable version of this, zpool get -H lowercase p, you can extract the information really nicely and be able to graph it. So if you extract that information every couple of minutes and compare it to the last value, then you can make a graph showing how busy each VDEV is. So you can understand how, if you have multiple VDEVs, how each one is doing, how each disk in that VDEV is contributing to the performance, and so on. All this information ZFS has been collecting the entire time. It just wasn't available to you, and now it is in a nice machine parsable format, but also human readable if you want it as well. As I mentioned, some of the stats from zpool status are available. So if we look at this output here of a zpool status on a pool, I've highlighted in different colors the different parts. So currently you can get the name of the pool and its state, is it healthy or degraded or whatever, from pool properties. And then with the new VDEV properties, you can get the list of all the VDEVs, whether they're online or degraded or replacing or whatever, and the error counters, the read, write, and checksum errors for each VDEV. So all the stuff in green is newly available. Currently, the stuff in gray is not available in a machine-readable format. You can try to parse this user, human-readable zpool status output, but it's not really conducive to pulling it out mechanically. So as a future project, I'd like to make all of those text strings available as properties as well. But it turns out most of these are constructed in user space after the fact, whereas properties are generated in the ioctl side, on the kernel side. So don't want to move all of the translation and so on into the kernel either, but someday I would like there to be a nice way to get the information about the status and what actions should be taken and so on of your pool as properties. And that scan line that tells us about a resilver that maybe is in progress right now, I would definitely want that broken up. I want to be able to see, I've resilvered so many megabytes, or I'm currently X% done, and the estimate is a separate field, and the number of errors is a separate field, and so on. So finding the right way to break that up is a future project. But you can at least now get a list of all the VDEVs and understand the hierarchy using the children parameter and the parent parameter, and all those counters. So has this ever happened to you? Because it has happened to me. You have a pool, in this case a RAID Z2 with 6 disks, and after a replacement or something, or just a device moving slots and changing names, one of your devices in your pool has chosen a different geom name than the rest. Right? So I have this disk DA3 that's being opened as just its partition number rather than via its GPT partition label. And so now it doesn't tell me its serial number as part of the label, and so on. If it was just a regular pool, it's not so hard to fix. You can zpool export and zpool import with the -d flag and tell it only look in /dev/gpt, and it will find the version of that label and be fine. But when it's your root pool, it's really annoying because you'd have to boot from the installer or a USB stick or something to do this dance of importing and exporting the pool and so on. So with VDEV properties, you can just zpool set the path back to the path you want, and that will get saved into the vdev config, and so next time the pool imports at boot, it will look for that name instead. It's mostly just me being overly finicky about how nice zpool status output looks, but over time, having the serial numbers of my disks in the zpool status and being able to match those up with physical labels on the outside of the hot swap bays has made my life so much better. And so when it's missing on one of the disks, it bothers me, and I don't want to have to reboot a bunch of times to fix it. So a little magic with vdev properties, and you can now control it that way. But sometimes you have a lot more information you want to keep about a disk. So that's where the vdev user properties come in. You can store any information you want about a disk. Each property can store up to 8 kilobytes of text. So you're probably more than enough, and that's per property. So if you need to store 16 kilobytes worth of stuff, you can just use a bunch of properties. Each one can store 8 kilobytes, and you can have as many of them as you want. I suppose there's a performance downside to having thousands of them on one disk, but the performance penalty will only be in trying to read all the properties, so not a big deal. We'll get to how the properties are stored in a minute, but what I want to spend most of the time talking about is what you can do with this. So obviously, I was using the GPT label from the partition table to put the serial number of the disk as part of the device name. But for various other reasons, you might want to store a bunch of information about the disk in the vdev property, including its serial number, because that can be useful for replacing the disk. Something data center operators don't like is when you point them at your server that has a lot of disks and say, I need you to replace the one that's not this list of serial numbers that is good, whatever one isn't that. Isn't so helpful, right? Because once a disk has died completely, you don't necessarily know what the serial number is anymore. You can't ask the disk what its serial number is at this point. And so if you know all the serial numbers of the disks that are working properly, you can be like, it's not these by process of elimination, but that's a lot more work. Whereas if you stored it as a property here, you'd be able to read it out even if the disk is gone. And so in addition to the serial number, which is useful for replacing it, you might want the model number or even a URL to buy the disk or whatever, so that when it's time to replace that disk, you know where you can get it. Whether that's a part number or a SKU, a model name, whatever information you want to put in there that might be useful. Even the link to Newegg or Amazon or something to order the replacement. This is the exact model. We want to get the same thing if we can. Another thing I've done with it even is storing previously measured performance data. So I've done some tests on this disk, and I know it should be able to read this many IOPS, or should be at least this many megabytes per second, or this fast. And then later, if it's not doing that, I can compare that and be like, okay, I'm going to perform that same test now, and if the disk is significantly slower, I know something is wrong. But I didn't have to go find some notes or something. I actually wrote that information as part of the vdev, and so I can pull that out whenever I want and have access to that information. On the next slide, I'll even show a handy trick for storing the partition layout. You can have ZFS automatically replace the disks. So if you're using ZFS-D and you're not partitioning your disks, ZFS-D can automatically do things like, oh, I noticed the disk in slot 13 was just removed and a new disk was put in, and that disk is blank. Okay, I can trigger a zpool replace and replace the missing disk with this new disk that has been put in its slot. But that doesn't work when you partition the disks. And sometimes you partition the disk because you want to boot off of them, and that's how you would do that. Or you have various other things going on the system, or you just want some raw swap, or whatever. But it means that when you want to replace that disk, you want to recreate the partition table. And if you want all of that information, wouldn't it be handy if it just was there as part of the VDEV. And then lastly, something I've started doing is keeping track of the warranty date for a disk. So I can even have my monitoring system, once a week, check all the disks and be like, hey, are any of these going to be out of warranty in the next couple of weeks? If so, I need an alert so I know I got to order some replacement disks and start swapping out these that are beyond their warranty lifetime. Or even just a disk failed. Was it still within warranty? Yes. Okay, then I'll start the RMA process. And if not, okay, I'm on the hook to pay for the replacement. So as I mentioned, each VDEV property can store 8 kilobytes of information. So in this case, I can just zpool set, systems.klara::partition table equals, and shell out to gpart backup and the disk. And gpart will return a serialized text of that disk's partition table. It's multiple lines, so I quoted it here, but ZFS doesn't care. It's just 8 kilobytes of arbitrary text. And so I set that on the disk for each of my disks, and then down the road, disk has failed. I've physically swapped out the bad disk with a new disk. So now I can just zpool get the value of the property again, and immediately pipe that into gpart restore. And now the new disk is partitioned with the exact same partition table settings as the old disk, and then zpool replace the old disk with the new partition name, and my pool starts resilvering and everything is great. So how do those actually get stored? So VDEV properties are stored in a per-vdev ZAP, or ZFS attribute processor. ZAPs are a key value store mechanism that's built into ZFS. It's actually what's used for directories and properties on datasets. So properties on datasets are stored in this way. It's just a key value pair. But directories actually work this way. Each directory is basically just a key value store of the file name to an inode or object number, a ZFS object number. And so a directory is just a giant list of all the names of the files or directories in there and a pointer to the object number. Luckily, the concept of a per-vdev ZAP had already existed. As part of the device removal code, each VDEV grew a ZAP to keep track of progress if it was being removed, and some other ancillary things. So that means that VDEV properties didn't require a new feature flag because the VDEV per-vdev ZAP was already there, and we could just add additional values to it. Some of those counters we talked about before, like the IOPS and the bytes counters, and a lot of the read-only things that just come from ZFS's internal state about the VDEV, do not persist, so they're not written to the disk. Only the changes you make to the writable property, and for example, the path writable property actually lives in the VDEV config, not in this property ZAP. And then any of the user properties do live in this ZAP. And all the VDEVs have properties, even the things that aren't really a disk. For example, like we talked about earlier, if you have a RAID Z VDEV, if you use zpool status, you'll see the pool name and it says, RAID Z 3-0, and then under it are a bunch of disks. Each of those disks has some properties, but the RAID Z device itself has properties, including a list of all the disks that are children of it. And so that means you can set properties at both those different levels. Currently, there's no inheritance. So if you set a property on the RAID Z, each of the disks under it doesn't inherit those properties. We're not sure yet whether it would be useful to have inheritance. Right now, it would be a bunch of extra complexity. But especially when we start thinking about how we want to do the VDEV queuing code, where we say, how many asynchronous reads do we queue to this device at once to avoid creating too big of a backlog. A number you want to be higher on flash-based disks to get more performance, but not high on hard drive based pools to avoid creating a lot of latency. In that case, you could see where you might want to set it on the top level VDEV and have it be inherited by the disks underneath. But that's one kind of weird case, and especially because of the way the VDEVs work, we would likely not actually need to inherit it. It would just not apply to the leaf disks and only apply to top level VDEVs, because that's where all the device queuing stuff happens anyway. But if you have an idea for a property, I'd love to hear about it. And if it makes sense to have inheritance, then it's probably something we could look at. So as I mentioned, I originally presented this idea at the OpenZFS Developer Summit in 2018 at the hackathon, and then I started a breakout group, and a bunch of us went to a room with a whiteboard and worked out how we would do this. We had a couple of different ideas about how we would do the command line interface. I think originally we had it look more like zpool set disk at property equals or property at disk equals, but we settled on this other mechanism instead because it was cleaner. But then I developed the initial version of this, but I did this directly in ZFS back before OpenZFS 2.0. And as you might have noticed, all the ZFS code in FreeBSD moved from sys cddl OpenSolaris UTS common FS ZFS to like sys contrib OpenZFS. And all the paths changed a lot. That was going to be a real pain to move all my new code, especially because I wrote it when FreeBSD was using SVN even. It was going to be a real nightmare to try to reapply all of those changes to all those different files that are all in different places. And the fact that it was kind of one giant SVN blob still. But luckily, I could check out Git from the same point as my SVN and commit the patch there, and then pull that over into the OpenZFS repo and use Git's inexact rename detection after changing the Git config to allow a much bigger amount of time and files to be compared. And it found almost all the files and applied my patches correctly. And it only took a little bit of fixing up to get that all applied to the new repo. Once that was drafted and posted, it got review, and it turned out that very much like the original idea back in 2018, but at this point it was 2021, Mark Mabey from Delphix was working on finishing up the queued device removal feature. So if you remember a couple of years ago, ZFS gained the ability to evacuate a VDEV. So if you have a disk that's a plain stripe or a mirror, so anything that's not a RAID Z or a DRAID, then it can be removed from the pool now. You can actually shrink a pool, and the way it works is it takes this new disk, or the disk you're trying to remove, marks it as removing, which is one of the new properties we talked about, and then it, in large batches, relocates the data off the disk that's being removed to another VDEV and keeps an indirection table that ZFS keeps in memory and writes to disk so that it can reload. But keeps in memory so that when you try to read from the VDEV that's now been removed, you just get an indirection saying, oh, that block is now on this other VDEV at this other offset. That's great to remove a disk, but sometimes you have a bigger pool and you want to remove 2 or 3 disks. Well, you can only do one at a time in ZFS. But the problem being, if you remove the first one, some fraction, if you have a 6-disk pool and you're removing 2 of the disks, when you're removing the first disk, about 1/5 of the data is going to get written to the disk you plan to remove next. And so then when you remove that one, you're removing that same 20% of the pool to yet another location and creating more indirection. So this feature allows you to set allocating to off on a disk, and when you do that, all of the space on that disk is removed from the pool, and it means that when you're removing other disks, it won't get written there, and you can queue up devices for removal. We'll talk more about that in a minute. But importantly, all the VDEV properties feature is completed and it's been merged into OpenZFS master. It was a bit late for 2.1, but basically the next time there's an OpenZFS release, it will include this feature, or you can use the development branch now. So as I promised, talking more about the allocating property. With device evacuation, you want to avoid moving the same data multiple times. So you can set allocating equals off on the two disks you're about to remove, which to successfully set allocating to off, ZFS will make sure there's actually going to be enough room that removing the disk will succeed. And so as soon as you set allocating off, the pool will shrink its free space to account for that. And that allows you to also more easily see the impact of your device removals, but make sure that they're not going to fail partway through or something. So you can set allocating goes off on those 2 or 3 VDEVs you want to remove. Then you remove them one at a time, but you know that no new data is going to get moved to the disks you plan to remove next, saving a lot of time and a lot of useless writes, especially if you're doing this in the cloud and you're paying for the data transfer. You don't want to be transferring the same data multiple times if you can avoid it. And ZFS will also make sure you have at least one allocatable device in your pool. If you want to make a pool read-only, this is not the right way to do it. So that leads to the interesting question, what else could we do to make this more useful? What use cases do you have for it? One of the next things we'd like to do is get ZFS channel programs integration done for this, so that it's easy to read and write and set multiple properties and so on. If you're going to set 10 user properties on each VDEV as part of setting up the pool, being able to do that as one transaction instead of 10 times each disk would be much more efficient. A really interesting one is this idea of a mirror read bias. So imagine you have a mirror on your ZFS pool, but one of the disks that's in this mirror is actually like a HAST device or iSCSI or something, and is actually a physical disk in another server on the other side of the city, like on a MetroNet or something. So it's only a couple of milliseconds away, but it's far enough away that it's going to be slightly slower, and there's going to be some limit on how much transfer it can do. What if you could set a property on the mirror that says, if the host name of the machine is X, then always try to read from this, member A of the mirror. But if the host name of the machine is Y, then always try to read from member B. So this way, if you have some kind of a failover setup, you could teach ZFS to, all writes should go to both disks, so there's a mirror. But when you're reading, you probably want to read from the local disks only, which there might be more than one, right? If you have a 4-deep mirror, 2 of the drives are local and 2 are remote or something, you want to use all the bandwidth that's available from your local disks, but you don't want to read from the remote disks that are slower because you probably have more than enough capacity with the local disks. But this isn't just saying always use one specific part of the mirror, but saying, depending on the host ID or something, it could change which disk is the one you want to read from. But you could also use this in something like a laptop. Not my current laptop, but my previous one had one SSD and one hard drive. And I actually mirrored them in ZFS because it was the best I could do in that machine. But I might want to tell it, hey, always read from the SSD, because my reads are mostly random and the SSD will be able to do that plenty fast. But the writes in ZFS are not random. They're all batched up into a big chunk and written to the disk. So the hard drive would be able to almost keep up with the SSD. It would do 100 megabytes a second or more anyway. So you could do something like this read bias even inside a machine with just 2 different types of disks and just say always read from the fast disk, but when we're writing, we can write to both. Another thing that might be interesting at some point is doing property caching. Currently, libzfs does this for pool properties. So as soon as you open a pool with libzfs, it loads the properties once and then just returns them to you as you try to read them without having to do an ioctl into the kernel to be like, hey, what's the value of this property? I don't know that we want to do it by default and just load all the properties of all the VDEVs as soon as you open a libzfs handle. But maybe once you start reading the properties of a VDEV, libzfs should keep that information so that you don't keep doing a bunch of separate ioctls. But in the end, we're not that concerned about the performance of VDEV properties because we don't intend to be using them in time-sensitive use paths. But it might actually be useful, especially if you start doing this a lot, to have some caching there. And as we talked about earlier, would it be useful to have inheritance on the properties, especially since there already is this kind of hierarchy of your VDEVs where there are parents and children and so on? Should the children inherit some of the properties? How would that work for user properties and so on? And then another idea was potentially we could persist some of those non-persistent counters. So for example, the number of IOPS, or importantly for, say, tracking wear leveling on an SSD, the total number of bytes written to the disk. We wouldn't want to flesh that out frequently, but if we could set some checkpoint and just update the value that's persisted on the VDEV like once an hour, would that be useful? Most disks are going to have something like a smart or something that's going to provide counters for that, but not all of them do. Although it's also weird because of the way VDEVs work, some of those values would persist across the VDEV being replaced, right? If you swap out a failed disk, should the counters go back to 0 or should they persist? Because I guess that's something I didn't mention earlier. Because the properties are stored in a ZAP, that's pool metadata. So that persists even if the disk is disconnected. So if you pull a disk out of the array, you will still be able to read its properties because those properties are stored across the whole pool with the same redundancy as your user data. So that's what makes it useful. You can find the serial number of the disk even once the disk is removed. So some closing thoughts. What other settings would you like to have as VDEV properties? Are there other things that ZFS knows about the disk that we could expose? Are there other things you'd like to be able to control about how ZFS uses each disk? For example, in the original fault management tool on Solaris, there was a configuration in the tool that defined, how many checksum errors on this disk in X amount of time before we should automatically trigger replacing the disk with the spare. Should that be a per-vdev setting instead of a system-wide setting or just a configuration of the fault framework? I'm not sure ZFSD works exactly that way, but maybe it should. So what other stuff would you like to see as VDEV properties? One of those that I thought of is we have these new special VDEVs that you can use for storing metadata or small blocks or dedupe and so on. Should what types of data could be written to this special VDEV be controlled by a VDEV property? So you can set what size of small blocks should go to the special VDEV on a per dataset level. But if you have multiple special VDEVs, maybe you want one of them to be metadata only and one to be small blocks only. Or, you don't want anything but dedupe going to the dedupe special VDEV, and then you have a regular special VDEV for your metadata, and being able to control all of that with per-vdev properties. But as this work continues, it raises the question, how many properties is too many properties? As it was when I showed that slide earlier with the zpool get output, I had to trim a bunch of the less interesting properties to make it fit on a slide on a font size that was readable. So at what point do we have too many properties and we shouldn't keep adding more, or we should be more picky about what properties we expose? And that also raises the question, should you be able to set some of the VDEV properties at pool creation time? So if you're going to put a bunch of information about each VDEV in the VDEV properties, maybe you want to do that as part of the zpool create command instead of a bunch of follow-up actions after you create the pool. But how do we make a command line interface for that doesn't get really hard to reason about? And getting back to the idea of too many properties, should we add a new type of property that's not hidden like we do for some of the binary properties like the encryption key and so on, but maybe ones that don't show up when you do get all, but do show up if you do get the specific name? But if we do that, do we need a special version of alls, like get really all or something, to make sure you get all those hidden properties? But I'd love to hear people's ideas, so you can get in touch. So if you want to have work done on your ZFS, or if you have trouble with your pool, or you'd like to see custom ZFS features developed, you could reach out to our company via that email address or our website, or hit us up on Twitter. Or if you just have comments about my talk, then you can hit me up on Twitter, and we can talk about it. So thank you very much.